everybody, and welcome to my talk today at the 4th Maldives Marine Science Symposium. My name is Lucy Carruthers. I'm a second year PhD student at Northumbria University in the UK. And today I'm going to discuss my project, which is a multidisciplinary investigation into mangrove health in the Maldives using remote sensing and geochemical techniques. And before I get started, I'd just love to draw your attention to the mangrove forest in the background, which is on Hitadu in Lama Atoll, and I had the absolute pleasure of visiting there when I was on fieldwork. I got to kayak around the channels and see some baby sharks, and it's such a beautiful place, and I highly recommend going to see it if you can. Just a brief overview of the structure of today's presentation. So we'll have a short introduction into mangroves in the Maldives, and then this presentation is split into two halves. So the first part is the remote sensing aspect of this project, and then the second part is the geochemical aspect. I'll then discuss some take-home messages from the results that we have so far, and as this project is ongoing, I will then discuss the future work we have in the pipeline at the end. So, mangrove forests. So they exist in the intertidal zone of tropical and subtropical environments. They provide many economic and ecological ecosystem services such as fisheries production, shoreline change protection and carbon storage. And globally, the economic valuation of mangrove ecosystem service is $194,000 per hectare per year. So they have high socio-economic and ecological value. 15 species of mangroves exist in the Maldives and are found on at least 150 islands, occurring mainly in the northernmost and southernmost atolls. Now, mangroves in the Maldives develop in two ways, either as depressions, where there's little or no connection to the seawater, but they receive water flowing through porous coral rock, or as open bay mangroves, which are connected to the sea by channels. Now, the mangroves on Hitadu are a great example of this. Now, mangroves are highly important ecosystems in the Maldives for many different reasons. So they are crucial for protection of low-lying islands against sea level rise, flooding and erosion. Mangroves are organic rich carbon sinks, and mangrove deterioration could turn them into carbon sources. And they're really important nursery habitats, and a survey in 2020 on mangrove forests in two different islands found a high number of juvenile sharks and rays, juveniles of commercially important fish in both bays, and juvenile sickle fin lemon sharks at one of the bays, which is a vulnerable IUCN species. At the beginning of 2020, I'm not sure if anybody else in the audience saw these reports too, but reports began to appear on social media and in the news documenting mangrove die-offs on at least 11 islands, and the cause was unknown. Figure 2 shows various examples from different news reports reporting the die-offs. So in July 2021, we held a meeting between Northumbria University and Blue Marine Foundation, along with local NGOs to discuss the issue. We heard from the locals the extent of the die-offs, and they gave me some feedback on some initial research I did. And so here are some drone images of the mangrove die-offs I've been discussing from 3 different islands. So you can really see the extent of the issue and how it is affecting the vegetation on all of the islands. This brings me to the research rationale for this project, and after hearing reports in the media and the local knowledge and seeing the images of the die-offs, we felt we had to investigate because mangroves have high socio-economic and ecological value, the cause of the die-offs is still unknown, and there really is limited research of mangroves in the Maldives, so results from this study can help increase our understanding of such an important ecosystem. My overall aim for this project is to understand the spatio-temporal patterns of mangrove health and identify drivers influencing change, and I have 3 research questions. And they are, what are the temporal trends in mangrove health? What are the controls on mangrove health? And what is the relationship between mangrove health and carbon fluxes? Now we're at part 1 of this project, which is the remote sensing aspect. And the remote sensing work focuses on 7 study islands. So we have 6 in the north, and we have 1 island in the south. And we have 6 inhabited islands and 1 inhabited island. So we have quite a variety of different island types. Now, the first stage in the methodology for this project is mangrove mapping using Landsat images in Google Earth Engine. So I used images from 2014 to 2022 that have a 30-metre spatial resolution, and I created 2 cloud mass composite images per year in Google Earth Engine that have a cloud cover of less than 10%. So composite image 1 were the pixel average of all the images, now excuse my pronunciation, in the Uravi monsoon period, which runs from December to March. And composite 2 is the pixel average of all the images in the Hulahangu monsoon period, which runs from April to November. So I wanted to have a composite image from each season to take into consideration seasonality. Now, for those who are unfamiliar with composite imagery, this is an example here that I have drawn. So imagine these are all the Landsat images for the Uravi monsoon period in 2014. So I would pop these images into Google Earth Engine, and Google Earth Engine would take a pixel average of all of these images, and it would generate this one image here, which represents the pixel average of all the images in the Uravi monsoon period for 2014. The second part of this methodology was to create land cover classifications, and I did this in Erdas Imagine software using PlanetScope imagery, as it has a super high spatial resolution of 3 meters. And I created 4 classifications, which were water, beach and buildings, healthy vegetation, and mangrove die-off. And I used approximately 20 training sites per classification. And you can see from figure 4, this is an example of one of the island's 4 land cover classifications. The final stages in this methodology was to perform a normalised difference vegetation index for each island. So I exported the mangrove die-off classification as a shapefile and imported it into Google Earth Engine. I then ran a normalised difference vegetation index, or an NDVI, within the mangrove die-off area, and figure 5 is a great example of this. So what's an NDVI? Well, it's a measure of greenness, and values range from -1 to 1. So the higher the NDVI value, it infers healthy vegetation, and the lower the NDVI value suggests unhealthy vegetation. Once I generated these NDVI values, I plotted them against time to evaluate the temporal trends in mangrove health. So what did we find? Well, this is an example from Fado of the NDVI shapefile from Google Earth Engine. Now, on the left, we have the 2 monsoon periods, and below we have the year, so it ranges from 2015 all the way down to 2022. And if I can draw your attention to the legend here, so the light green and the green colours are higher NDVI values, so it's indicating healthier vegetation, and the white and the brown colours are lower NDVI values, so it's indicating unhealthy vegetation. Now, through time, from 2015 to the beginning of 2020, we see this dark colours, so it's a higher NDVI value, so it's indicating healthier vegetation. Now, something has happened towards the end of 2020. These white and brown pixels are appearing, lower NDVI values, unhealthy vegetation. And it's also progressively getting worse through time. You can also see that the decline in mangrove health is happening near the ocean side of the island, which is perhaps indicating that there is a relationship between sea level trends and mangrove health decline. Figure 7 describes the temporal trends in NDVI for each island in this study. So on the y-axis we have NDVI, and on the x-axis we have year. Now that goes from 2014 to 2022. So as you can see, from 2014 onwards, NDVI was relatively high for each island. However, in 2020, which is indicated by the purple dashed line, NDVI values decreased significantly for all islands across both monsoon periods, signifying a decline in mangrove health. This now brings us to part 2 of this presentation, which is the geochemical aspects of this project. Part of the project has taken us to Hodehu, which is in Huvadu Atoll, and we visited there at the beginning of this year in April, and we met with Areesh Abdulla from Huvadu Aid, who was super helpful with his time and his local knowledge. Now, the mangrove forests on this island are located in the orange box, so they are the west of the island, on the ocean side. So these are some images that we took from the mangrove area on the island, and you can really see the extent of the die-off. Now, it was the orange mangroves that were significantly impacted and declining health-wise, but upon investigation we also discovered that the black mangrove species were dying too. For this part of the project, we took some groundwater samples to assess the relationship between groundwater quality and mangrove health. So we went to 23 different sampling points across the island and we sampled from wells and taps. We had 2 probes to do some in-field measurements, and they were temperature, pH, electrical conductivity, total dissolved solids and salinity. And then we took the rest of the samples back to Northumbria University to assess for the various parameters outlined below. Results were then compared against the World Health Organization drinking water quality guidelines. So what did we find? Well, we tested for 25 different parameters, and I don't have the time to discuss them all with you here today, but here are 3 parameters which have significant findings. We have electrical conductivity, chloride, and total dissolved solids. Now, the mangrove forests are in the orange boxes, and the green dots are the groundwater sampling points. And what I'd like to highlight to you is that at the sampling points located nearby the mangrove forest, elevated levels of electrical conductivity, chloride and total dissolved solids were identified. Now this infers that groundwater nearby the mangroves is elevated in salinity. So what are the take-home messages from this work so far? Well, for mangrove health, we have found that seasonal oscillations in NDVI occur for all islands from 2014 to 2022. However, from 2020 onwards, mangrove health has decreased significantly for both monsoon periods across all islands. For the water quality aspect, we found elevated levels of total dissolved solids, electrical conductivity and chloride nearby the mangrove forests, which suggests hypersalinity from saltwater intrusion may be driving mangrove health decline. As this work is ongoing, we do have future work in the pipeline, which I'll briefly discuss with you today. For the remote sensing aspect of this project, now I have generated the NDVI values for all the islands across the time period. I'm going to then do some statistical analysis of different parameters. So I'm going to look at sea level trends, precipitation trends, and look at some elevation data. For the geochemical aspect of this project, we took some sediment cores from healthy and non-healthy zones. And in these cores, I'm going to look at carbon, iron, chromium reducible sulfur and do some lead-210 dating. We also took some gas samples from healthy and non-healthy zones. And within these gas samples, I'm going to look at methane and carbon dioxide. And we also took some cross-sections from healthy and non-healthy zones. And in these cross-sections, I'm going to look at iron and carbon-13. So this brings me to the end of my presentation today. Thank you so much for listening. I hope you found it interesting. And if you have any questions or would like to discuss this further with me, then please contact me at my email address below. Thank you very much.